And I copy y minus y1 equals the slope times x minus x1. I replace 8 and 5,120 and 1408. Did we get the same thing? Yes? Any questions? Can I just write it, or do I need to multiply? Do I need? Are we okay? Everyone? So you multiply 1408 times 8 and you add 5120, and I think I'm okay. So that's my G in Maple 1408x minus 6144. And that's the equation of the line. And this, as I said, I changed, as you see, I changed the x and the y's. I only wanted to see between 6 and 10, and I wanted to see only between 4,000 and 6,000. So I zoomed in to see the behavior of the tangent and the function, and they were similar. Very good. Moving on. I have another little video for you that I would like to, and that's the last one tonight. The last video tonight. Because I really liked it. I really liked it's only 3 minutes long. Why am I having difficulties with this sound here?
Between 2 points. So in this graph, this is our first point. Define the average rate of change, and then determine the average rate of change of a function. Looking at this graph here, this black line is a secant line. A secant line is a linear approximation of a function between 2 points. So in this graph, this is our first point, and this is our second point. The slope of this secant line represents the average rate of change of the function between these 2 points. So when you're asked to determine the average rate of change of a function, you're really just finding the slope of a line. Remember, the equation for the slope of a line given 2 points is m equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. So again, when you're finding the average rate of change of a function, you're really just determining the slope.
We know this. I'm just going to try to go.
The time and distance traveled on our trip, the graph might look something like this. Notice how at certain times the distance traveled is less than at other times. Meaning when the graph is steep, we're traveling faster. When the graph flattens out or doesn't increase as fast, our speed would be slower. So if we pick 2 points on this graph and sketch the secant line, the slope of that line would be our average rate of change on that given interval of time. So for example, if we look at the secant line from where we started to where we end, the slope of this red secant line will be approximately 69 miles per hour. But if we were to pick 2 different times on this trip, let's say at 2 hours and then at 3 hours, the slope of this secant line would give us our average speed during this time interval. Notice that our average speed from 2 to 3 hours would be less than the average speed of the entire trip. And you can see because it looks like we may have stopped to get gas or maybe at a rest stop somewhere around this time. Let's take a look at a few of our own examples. Let's determine the average rate of change of the given function.
It's what I wanted to show you, and I'm posting these videos for you on the website as well, in Canvas. So you have them in case you want to go back to them at any point in time. Okay? So we can find the average rate of change of a function from its graph. Yes, I had the function, but we can still approximate quite accurately, even if we don't have the function and we just have the graph. So that's one way of determining the average rate of change. Here's another way. What if I am given a table? And I just would like to go to our book, page 7 if you have it, and look at a table. So I am given in that particular situation, I started my video, right? Yes, I did. So on page 86, so problem 7, page 86, I'm going to quickly copy the table that we are given. So t is in seconds and distance is in meters. 0, 0, 1, 1.4, 2, 5.1, 3, 10.7, 4, 17.7, and 5, 25.8. We're asked, in this problem, we're asked to determine the average rate, the average velocity or the average rate of change, same thing, for each time period. So they wanted 1, 3, they wanted 2, 3, they wanted 3, 5, and we wanted 3, 4. Who will be responsible for 1, 3? Very good. Who will be responsible for 2, 3? Perfect. Who is responsible for 3, 5? Perfect. And I need somebody for 3, 4. Ben. Very good. So the average rate of change, average rate of change, and average rate of change. So between 1 and 3, 10.7 minus 1.4 over 3 minus 1. And so on and so forth. I just need the numbers now. So this is how we find the average rate of change, and we will come up with an idea of the instantaneous rate of change. This one? 4.65 doesn't mean anything without. Very good. Very good. Second one?
5.6 meters per second.
Third one?
7.55 meters per second. 7 meters.
Very good. Perfect. Now, here's part B. Use the graph of S, which is the distance, as a function of t to estimate the instantaneous velocity when t equals 3. Here it is. So I see that distance goes from 0 to roughly 25. So I'm going to use 10, 20, or maybe 5. I would say maybe 5, 10, 15, 20, 25. So 5, 10, 15, 20, 25. And from 0 to 5, 1, 2, 3, 4, 5. So this is in seconds, and this is in meters. Okay, that's my x-axis, that's my y-axis. So I'm going to try to plot these points. Now, it is very important how I choose the unit, because the graph may be distorted depending on the relationship here. I kind of use the same kind of unit between 1 and 2 and in between 0 and 5. So we'll see what I get. So 0, 0 is this point. 1 comma 1.4. If this is 2, I'm going to say roughly here. 2, 5.1, somewhere here. 3, 10.7, I'm going to say somewhere here. 4, 17, so 15, that's 17 and a half, so somewhere here. And 25.8. Okay. So I do have, so the question is, what happens at 3 in the book? So this is our target. Oh, that doesn't work. So here's our target. We want to determine the instantaneous velocity at 3. So if I were to graph, if my graph is correct, I were to graph something like this, then the instantaneous velocity at this point is the rate of change of the distance with respect to time at 3, which is going to be the same with a tangent line to the graph of the function at 3. So if I graph the function, I don't want to graph it because I want to show you something else before I do that, then this line, which is tangent at 3, will give us, the slope of that line will give us the instantaneous velocity at that point. Are you with me? So here's what we have. We have that in between 1 and 3, 2 and 3, 3 and 4, and 3 and 5. I am going to only represent on my graph as accurately as possible the slope of the secant line between 2 and 3, left and 3, and right and 3. So between 2 and 3 and 3 and 4, left and right of 3. So between 2 and 3, 5.6. So if this is 1 and this is 1, this will be a slope of 1. How will I graph a slope of 5.6? So the rise will be 5, roughly, and the run will be 1, right? So in my example, it's way too big, so let me just do this, 1 and 1, but you understand the idea. So now I need the rise to be 5. 2, 3, 4, 5. So this will be a line with a slope of 5, because this is a line with a slope of 1. It's 1 over 1. And this is a line with a slope of roughly 5. 5 over 1, right? 5 times this height, and still 1 here, right? So in order to graph between 2 and 3, a line with a slope of 5, well, I will have to say that because the whole thing is distorted, obviously I have 1 here and I have 5 here. It's not going to look exactly like this. So this is the slope of 5.6 in this graph. So the slope of this line is 5.6 meters per second. Now between 2 and 3. Now between 3 and 4, it will be this slope. So this will be between 3 and 4, 7. Obviously higher, right? So a slope of 7 should be something like this in a perfect graph, which I don't have a perfect graph. But I think you understood the idea, right? Rise over run. Now, how do I determine, how do I estimate the slope of the tangent line, which I'm going to graph? Let me see if I have, what is my green? Oh, brown is good too. So this will be the slope of the tangent line. Difficult to see. Slope of tangent at 3. How do I estimate that? Normally for quadratic functions, this appears to be kind of a quadratic function. All we have to do is to average the left and right. So this slope and this slope, I'm going to add them up and divide by 2. That would be a good estimate. An estimate still, but a good estimate. So the 5.6 between 2 and 3, and the 3 in the next one, which is 7. So the instantaneous I went to write. The instantaneous rate of change at t equals 3 seconds is approximately 5.6 plus 7 divided by 2. And of course, meters per second. How much is that? 12, right? 0.6 divided by 2, 6.3 meters per second. And if you're going to ask, wait a minute, will that work for all functions? I will say no. Estimating it left and right like that, no. Okay. I still have time. I was hoping to finish these two so we can discuss these two concepts here. But let me, both are very important. Let's start with problem 8. Since I only have 12 minutes left, I will not be able to do the last problem, but we can do it on. By the way, we do not meet on Monday because of Labor Day. I'm sorry. Okay, problem 8. The displacement, distance in other words, in centimeters of a particle moving back and forth along a straight line is given. So this is problem 8 on page 86. Is given by the equation of motion, S. I would write S of t. They didn't. I would write S of t. 2 sine pi t plus 3 cosine pi t, where t is measured in seconds. So S is measured in centimeters and t in seconds. Perfect. Find the average velocity during each time period. 1, 2, 1, 1.1, 1, 1.01, 1, 1.001. Yes, please.
The second one, what does that say?
S is in centimeters and t in seconds.
Is that 2 sine pi t?
It's 2 sine pi t plus 3 cosine pi t. Sorry about my handwriting. I apologize for that. But always stop me if you don't understand something. Don't copy the chart because I didn't put it in correct order. I started looking at it, and so from left to right. Actually, it was in order. It was. Sorry about that. It is in ascending order from left to right. That's all I wanted. Since I crossed it out, let me read. I should have left room for the left-hand side to explain something, but I didn't. Okay, that's okay. Now, what is the issue here? What are we trying to do? So it is this function. I'm not going to graph it, but we are given this function. Let's assume this is the S of t. And somewhere there is, on this graph, there is t equals 1. right? So this is t equals 1. Correct? So we're asked to find the average rate of change between 1 and 2. And I'm going to say this is 2. How will I determine the average rate of change between 1 and 2? S of 2 minus S of 1 over 2 minus 1. And it will be the same with the slope of this line. Correct? Perfect. Now I want to determine the next one. But 1.1, I'm going to say, is here. So this will be a new slope, right? A new secant line, right? Between these 2 points. How will I determine this one? This is the second one in red. The first one is in blue. How will I determine this one? S of 1.1 minus S of 1 over 1.1 minus 1. Perfect. Now I will be determining what? The next one in green, which is much closer, and it will be this point. So this will be this tangent, this secant line, which will be the average rate of change between 1 and 1.01. And then I'll get even closer, and I will get this one. Correct? Perfect. Can anyone create a function for me that will help us determine all those average velocities? Can anyone say, okay, I see that the reference point is 1. So this is the point that changes. It's here at 2 first. It's here at 1.1, then it's at 1.01, and then it's at 1.001. So can anyone give us a function? I'm going to call this function m, and it will be the slope of this line between 1 and 2, between 1 and 1.1, between 1 and 1.101, and between 1 and 1.001. One more time. Between 1 and 2, between 1 and 1.1, between 1 and 1.01, and in between 1 and 1.001. What is the variable? Not 1. The variable is this one that changes, getting closer and closer to 1. So I will write S of t minus S of the fixed point that does not change in any of those, S of 1 over, must be t, and must be 1. This is what I want to put in the graphing calculator. So in y equals, I know where to put this function carefully, how we would put it in, S of t, 2, sine, in parentheses, pi, x, there is no t in the calculator, minus, I'm sorry, plus first, plus 3, yes, 3 cosine pi t pi x, close the parenthesis, minus S of 1. Can anyone determine S of 1? We can put it in as S of 1, but I would like to determine it. How much is sine pi? Maybe I should do this on paper here, because I want to determine this number. So sine S of 1, 2 sine pi plus 3 cosine pi. Sine pi on the unit circle is right here. 0. Cosine pi. Excellent. So this is -3. So I will replace this number by -3 from the beginning. With minus in front, it's +3. Plus 3. Close the parenthesis for the numerator. And now I divide by what? In parentheses, of course. I divide by? Excellent. Thank you. X minus 1. And close the parenthesis. This is the function that will give us the slope for any change in t. 2, 1.1, 1.01, 1.001. So what should I do next? Go to second? No. Go to second and table and plug in 2, enter. Please. Okay. Don't forget to look at the mode. It's radian, that's good. And don't forget to go to second and table set. They changed all my settings because they updated the computer. Okay, it has to be in the ask mode. So, enter. Yes, I said yes. And yes, please.
It's there, it's not.
So, okay. Normally it goes back to, okay, never mind. So 2, enter. 1.1, enter. 1.01, enter. 1.001, enter. So, the first, so that's the M. That's why I left it open. So, what is the slope between 1 and 2? 6. Between 1 and 1.1, -4.712. Between 1 and 1.01, -6.134. Between 1 and 1.001, -6.268. Which of these is the best estimate of the instantaneous velocity at 1? Right. What if I do this? What if I want to get even closer? 1.0000001. Will this be an even better estimate of the slope of the tangent line at that point? Because now it's the secant line between extremely close points. Very good. Let's see what we get. What if I go even closer? 1.00000000001. I'm so close to 1. Can I put in 1 in there? Just 1? Why? What will I get if I just put 1? Of course, because it's undefined. The denominator is 0. Good, so I'm getting even closer. What do you think I'm going to get when I press enter? Same thing, I'm already there. Right? I mean, it's very, very close. It's considering even 1. So, -6.2. See, the calculator is not even that sophisticated to even write it. There's no room, right? 1.0001. So, to answer the final question, estimate the instantaneous velocity of the particle when t is 1. And I'll stop. What will you say? The instantaneous velocity at t equals 1 seconds is negative. Yes, -6.2, which means the particle is coming back. It doesn't mean that the velocity is negative. Going in the positive direction, the velocity is positive. Coming back, the particle is coming back. It just gives us the direction. -6.2 centimeters per second. Forgive me for holding you over 1 minute. I